How do you find statistics about criminal justice?
One of the best places to find statistics about criminal justice is the Bureau of Justice Statistics. The Bureau offers a multitude of useful crime statistics, including criminal victimization, crime characteristics, victim characteristics, and incident-based statistics, all of which help the police and other crime-fighting agencies to better understand crime and how it works. But the statistics don't stop there. There are also statistics about law enforcement officers, campus law enforcement agencies, and crime labs, a census of law enforcement training academies, and even statistics about the courts and criminal sentencing. There are also other places to find such statistics. For example, the Federal Bureau of Investigation offers statistical reports, such as the Uniform Crime Reports. UCR, a program started in 1929 that collects information about crimes reported to the police. But in the late 1980s, in response to law enforcement's need for more flexible, in-depth data, the UCR program evolved into the National Incident-Based Reporting System, NIBRS. This more complete system collects detailed statistical data on each reported crime incident and is used by law enforcement, researchers, governmental planners, criminal justice students, and the general public.
What are the foundations of mathematics?
The foundations of mathematics include how to formulate and analyze the language. You have to speak the right mathematical language to make meaningful mathematical statements, axioms. A statement accepted as true without proof, and developing logical methods in all mathematical studies. The most basic mathematical concepts in the foundations include numbers, shapes, sets, functions, algorithms, axioms, definitions, and proofs.
How can the accuracy of a mathematical model be determined?
There is usually one good way to determine the accuracy of a mathematical model. Once a set of equations has been built and solved, if the data generated by the equations agree or come close to the real data collected from the system, then we can determine its accuracy. In fact, the set of equations and models are only valid as long as the two sets of data are close. If a model result leads to conclusions that are not close to the real-world scenario, then the equations are further modified to correct for the discrepancies as much as possible. For example, in weather prognostication, meteorologists use various numerical models to make long-term predictions of weather systems. For more information about models and weather prediction, see Math in the Natural Sciences. It is interesting to see how meteorologists use a combination of several of the weather models to forecast the weather in certain spots around the United States. and the world mainly because no weather forecasting model has all the right answers. Every day, researchers are tweaking their respective weather models. Based on more collected data, in hopes of eventually understanding our weather a bit better.
What are time zones?
Time zones are any of the 24 regions on the globe, loosely divided by longitude but more erratic in their demarcations, which is divided according to the number of hours in a day. Within each zone, all clocks are set to the same time. Time zones include the International Date Line, an imaginary line of longitude generally 180 degrees east or west of the prime meridian. The date becomes 1 day earlier to the east of this line. Time zones are truly a product of mathematics. Initially, people used local solar time, resulting in slightly different times between towns. With technology, especially trains and telecommunications, more accurate timekeeping became a necessity. Thus, time zones helped solve many of the problems by setting the clocks of a region to the same mean solar time. The time zones made it easy for neighboring time zones to be labeled 1 hour apart. Not that the system is perfect. The hour separation is not universal. And because they often follow political boundaries, the shapes of the time zones can be extremely irregular.
What are differential and ordinary differential equations?
Logically, a differential equation is one that contains differentials of a function, with these equations defining the relationship between a function and one or more derivatives of that function. More specifically, differential equations involve dependent variables and their derivatives with respect to the independent variables. To solve such equations means to find a continuous function of the independent variable that, along with its derivatives, satisfies the equation. An ordinary differential equation is one that involves only one independent variable.
What were Archimedes' greatest contributions to mathematics?
Historians consider Archimedes, c. 287 to 212 BCE, Hellenic, to be one of the greatest Greek mathematicians of the classic era. Known for his discovery of the hydrostatic principle, he also excelled in the mechanics of simple machines. Computed close limits on the value of pi by comparing polygons inscribed in and circumscribed about a circle. Worked out the formula to calculate the volume of a sphere and cylinder. And expanded on Eudoxus's method of exhaustion that would eventually lead to integral calculus. He also created a way of expressing any natural number, no matter how large. This was something that was not possible with Greek numerals. For more information about Archimedes, see mathematical analysis and geometry and trigonometry.
What are examples of unlucky and lucky numbers in different cultures?
The concept of lucky and unlucky numbers in various cultures abounds. As many people agree, it's actually the luck of the draw that determines a lucky or unlucky number. Some cultures have tried to attach good or bad fortunes to numbers. For example, in terms of good luck and fortune, the number 7 seems very popular in many cultures. It is the holy number, symbolizing God in all forms, and is considered sacred to many people. The Japanese, for instance, have 7 gods of good fortune. The Egyptian god Hathor can be 7 cows at once. And there are the 7 days of creation in the Bible. Actually, the seventh was a day of rest. On the other hand, the same number can represent something that is bad. For example, many mythological monsters have 7 heads, in Native American lore. The Sioux saltwater snake Unskula could only be killed by a blow to her 7th spot. And the 7 deadly sins avarice, envy, gluttony, lust, pride, sloth, and wrath is a Western cliché. One famous unlucky number is 13, which is thought by most Western people to be bad luck because of the connection between Judas Iscariot, the disciple and betrayer of Jesus, who was the 13th man in the room at the Last Supper. But in other places, such as Italy and China, 13 is considered lucky. Even ancient civilizations did not shy away from the number 13. In the Celtic and Native American systems of astrology, there were 13 lunar months in the year and 13 astrological signs.
What is Mohs scale of hardness?
Mohs scale of hardness, also seen as Mohs hardness scale, Mohs scale, or even erroneously as Mohs scale, was invented by German mineralogist Friedrich Mohs, 1773 to 1839. This arbitrary scale measures hardness or the scratch resistance of minerals and is often used as a quick way to help identify minerals in the field and laboratory. But the numbers assigned to the various minerals are not proportional to their actual scratch resistance. Thus, the main reason for using the scale is to know that a mineral with a lower number can be scratched by a mineral with a higher number. Although the Richter scale is mentioned most often in the media when a quake occurs, there is a more precise scale in use today that is based on the mathematics of motions caused by the earthquake. Called moment magnitude, this method uses a physical quantity related to the total energy released in the quake, which is called a moment. Seismologists can also deduce moment magnitude from a fault's geometry in the field or a seismogram reading. Scientists occasionally use moment magnitude when describing an earthquake event to the public. But because the concept is so difficult to explain, the number is often translated into the Richter scale.
What is algebra?
depending on whether one is a student or professional mathematician. The word can mean either of the following, both of which are further described elsewhere in this chapter. School algebra is what mathematicians refer to as the algebra we learn in middle and high school and call arithmetic. But for most people, algebra means solving polynomial equations with one or more variables. The solutions to such equations are often obtained by the operations of addition, subtraction, multiplication, division, raising to a power, and extracting a root. For more information about all these operations, see Math Basics. This also includes determining the properties of functions and graphs. But mathematicians use the word algebra most often in reference to the abstract study of number systems and operations within them, such as groups, rings, and invariant theory. This is called abstract algebra.
What are some life questions you can figure out using math?
There are many questions you can explore about your own body and age with mathematics. For example, approximately how many Sunday nights can you expect to sleep until you are 100 years old? Just take 100 years, minus your current age, and multiply that result by 52 weeks in a year with a Sunday. For example, if you are 25, the answer would be 125 x 52 equals 3. 900. How many of those will be good night's sleep is up to you. To calculate the number of times your heart has beaten since you were born, you need the help of a watch or clock. First, time your heartbeats per minute. To find out how to count your pulse, see Everyday Math. Then multiply beats per minute x 60 minutes, in an hour, x 24 hours, in a day, x 365.25 days, in a year, x your age. For example, 72 heartbeats x 60 x 24 x 365.25 x a person who is 30 equals 1,136,073. 600 beats since the person was born. Of course, this is an approximation, since the heart usually beats slower at night. And it speeds up when you see the bill for your latest car repair. Figuring out how much air you breathe during a lifetime is another fun mathematical calculation. If you optimistically decide you want to eventually be 100 years old, and the average person inhales about 1 pint, or 0.47 liters, of air per breath, you can do the math. First, take the number of breaths you take while at rest per minute, say about 21 per minute. X 0.47 liters x 60 minutes x 24 hours x 365.25 days x 100 years old equals 519,122,520 liters. Again, this is only an approximation.
How did money evolve?
Before the advent of money, exchanging goods was merely a matter of bartering. Livestock and grains often were used in ancient times as methods of barter, with one item exchanged for another. But there were definite limitations to this. For instance, if a farmer wanted to barter for a horse with wheat in the winter, he would have to know how to store the wheat in order to get the horse. Timing became essential, and sometimes meant the difference between surviving and dying. Some of the first types of money included limestone coins, ranging in size depending on their value. Tobacco, shells, whale's teeth, and even bread in medieval Iraq. The use of gold and silver coins is thought to have started around 650 BCE by the Lydians, who lived in the area between the Black and Mediterranean seas. Before that, metals were traded as money in other forms, such as nuggets, rings, and bracelets. Paper currency first appeared about 300 years ago and was usually backed by some standard materials of natural value, such as gold, that could be converted on demand. Using currency was a great improvement over the bartering system. Although bartering still has its place in many countries, especially throughout smaller communities. For example, when gold became a trade standard, it was easier for the farmer to buy the horse in the winter with gold coins than try to store enough wheat, and keep away mice, to make the trade. In the West, as more and more people participated in the gold standard, the banking industry grew, paralleling the growth of trade and industry. Today, monetary systems are deeply entrenched, with various types of currencies in a multitude of countries. Type of money keeps changing, too. For example, in 1988 the world's first durable plastic currency was introduced by Australia. Plastic bills were seen as a way to frustrate counterfeiting. In 2000 the European Economic Community introduced the euro, a monetary unit that puts much of Western Europe under a common currency. All this exchanging and changing of currency involves, of course, mathematics.
What is an axiomatic system?
An axiomatic system is a logical system that has a definite set of axioms. From these axioms, theorems can be derived. In each system, propositions, statements, are proved on the basis of a limited number of axioms or postulates, all with a few undefined terms. The other terms are defined on the basis of the undefined terms. One of the first axiomatic systems was Euclidean geometry. Overall, an axiomatic system has several basic components: the undefined terms of the system, primitives, well-formed formulas, or how symbols are put into the system based on certain allowed rules, sometimes called defined terms, axioms, or what is also known as self-evident truths of the system. Theorems, or statements that are proved based on axioms or other proven theorems, and finally, the rules of inference, or those that allow moves from certain formulas to other formulas.
What does point-slope equation of a line refer to in analytic geometry?
A point-slope equation of a line refers to Cartesian coordinates, if a point has coordinates x1, y1, on a line and a slope equal to m, then the equation y1 equals m, x1, is the point-slope equation. Point-slope is most often used when finding an equation of a line.
What is a mortgage?
A mortgage is a method of using property as security for the repayment of a loan. It is based on a 14th century coinage of a Latin word meaning dead pledge. The interpretation was that the property was dead to the borrower if he defaulted on the debt, and the pledge was dead to the lender after the loan was repaid. For centuries, it's been figured out using mathematics.
What are some other examples of dissection puzzles?
There are several other examples of dissection puzzles, including the following. The haberdasher problem, Pythagorean square puzzle, T-puzzle. Puzzle inventor Henry Ernest Dudney, 1857 to 1930. Of England, was instrumental in developing many more puzzles than the cryptarithmetic puzzle described above. One of the most famous of his geometrical puzzles is the haberdasher's problem, which asks how an equilateral triangle can be cut into 4 pieces and reassembled to form a square. His model used hinges that would move the pieces into place. In the Pythagorean square puzzle, the 2 squares on the left are combined to form a single large square on the right. The T-puzzle is a dissection puzzle that forms the letter T. 4 pieces are used to create the capital letter, as seen on P425.
What are axioms and postulates?
These two words are often treated as the same, in fact. Some mathematicians consider the word axiom a slightly archaic synonym for postulate. Although both are considered to be a proposition, statement. That is true without proof, there are subtle differences. An axiom in mathematics refers to a general statement that is true without proof, and it is often related to equality, such as 2 things equal to the same thing are equal to each other, and those related to operations. They should also be consistent. It should not be possible to deduce any contradictory statements from the axiom. A postulate is also a proposition, statement, that is true without proof, but it deals with a specific subject matter, such as the properties of geometric figures. Thus, it is not as general as an axiom. For example, Euclidean geometry is based on the 5 postulates known, of course, as Euclid's postulates. See below. For more about Euclid, see History of Mathematics and Geometry and Trigonometry.
What are some paradoxes that deal with space and time?
There are numerous paradoxes that deal with the counterintuitive aspects of continuous space and time. One of the most well-known is the dichotomy, or racetrack, paradox. Before an object can travel a distance d, it must keep traveling in halves. In terms of the racetrack, in order to reach the end of the course, a person would have to first reach the halfway mark, then the halfway mark of the remaining half, then the halfway mark of the final fourth, then of the final eighth, and so on ad infinitum, to infinity. Therefore, the distance can never truly be traveled to reach the end of the racetrack. The Achilles and the tortoise paradox is a version of the tortoise and the hare, but with a very different resolution than the well-known fable. In this paradox, Achilles gives the slower tortoise a head start. Achilles starts when the tortoise reaches point A. But by the time Achilles reaches A, the tortoise has already moved beyond that point to point B. When Achilles reaches B, the tortoise is at point C, and so on ad infinitum. Since this process goes on forever, Achilles can never catch up with the tortoise. Another paradox is the arrow paradox. In this case, an arrow in flight has a certain position at a given instant in time, but that is indistinguishable from a motionless arrow in the same position.
How is the slope measure and y-intercept of a line determined?
On a graph, the slope is the line in a plane completely specified by a point and a number. Mathematicians know that when an equation is written as y equals mx plus b, they can determine the slope measure and y-intercept, or slope-intercept, of the line. In this case, the m, or x coefficient, is called the slope measure and the y-intercept are the coordinates that solve the equation. For example, for y equals -2x plus 4, the slope measure is -2 and y-intercept is the coordinates, 0, 4. To test this result, replace the x with the first coordinate, 0. -2x 0 equals 0, therefore, 4 is left, resulting in y, or the y-intercept, being 4.
When was non-Euclidean geometry first announced?
Non-Euclidean geometry, or a system of geometry different from that developed by Euclid, cp. 17, was first announced by Russian mathematician Nikolai Ivanovich Lobachevsky, 1792–1856, also seen as Lobachevsky. In 1826. This idea had already been independently developed by the Hungarian János or Johann Bolyai, 1802–1860, in 1823 and by Carl Friedrich Gauss. 1777 to 1855, in 1816, but Lobachevsky was the first to publish on the subject. In 1854, German mathematician Georg Friedrich Bernhard Riemann. 1826 to 1866, presented several new general geometric principles. His suggestion of another form of non-Euclidean geometry further established this new way of looking at geometry. Riemann was also responsible for presenting the Riemann hypothesis, or zeta function, a complex function that remains an unsolved issue in mathematics today. For more information about geometry and Riemann, see geometry and trigonometry.
Is it possible to convert international units seen on such items as vitamin bottles to milligrams or micrograms?
No, there is no direct way to convert international units, IU, to mass units, such as milligrams. Most familiar to people who read vitamin and mineral bottles, an IU has nothing to do with weight. It is merely the measure of a drug or vitamin's potency or effect. Although it is possible to convert some items' IUs to a weight measurement, there is no consistent number. This is because not all materials weigh the same and the preparation of substances vary, making the total weights of one preparation differ from another. But there are some substances that can be converted, because for each substance there is an international agreement specifying the biological effect expected with a dose of 1 IU. For example, for vitamins, 1 IU of vitamin E equals 0.667 milligrams. mg, 1 IU of vitamin C is equal to 0.05 milligrams. In terms of drugs, 1 IU of standard preparation insulin represents 45.5 micrograms. 1 IU of standard preparation penicillin equals 0.6 micrograms.
What mathematical concept is used to calculate mortgage payments?
In most cases, a mortgage is based on amortization, which is the gradual elimination of a liability. A financial obligation or debt, such as a mortgage, in regular, fixed, systematic payments, such as monthly, over a specific period of time. These payments must be enough to cover both the principal borrowed and the interest. Although it is usually written in a complex set of mathematical calculations, simply put, amortization means a part of the payment goes toward the interest cost and the remainder goes toward the principal, or the amount borrowed. The interest is then recomputed on the amount owed, and therefore it gets smaller and smaller as the ending balance of the loan becomes less and less. That is why the homeowner pays a great deal toward interest and not the principal for the first several years of a home mortgage. For example, if a mortgage is taken out for $100,000 at 6.5% for 30 years, The fixed monthly principal and interest payment is $632.07. For the first month, the homeowner pays interest on the $100,000, or $541.67, with the remainder of the payment, $90.40, going toward principal. In other words, the debt on the principal is reduced by $90.40. By the next month, the homeowner owes interest on a lesser amount of money on $99,909.60, or $100,000 $90.40. Not the $100,000 with $541.18 going toward interest and $90.89 going toward principal. As payments are made month after month, the interest decreases and the principal reduction increases. By the 360th payment, or 30 years later, the payment contributes $3.41 to interest and $628.66 to principal.
What is a decimal system?
The decimal system uses the base 10 notation system to represent real numbers. A decimal expansion is the expression of a number within the decimal system, such as 1, 15, 359, 18.7, and 3.14159. Each number within the system is called a decimal digit. Such decimal notation or a numbering notation based on decimals was first used in India around the year 594. The decimal point is represented by a period placed to the right of a unit's place in a decimal number. It is interesting to note that a comma is used in continental Europe to denote a decimal point, such as 3,25, translated as 3.25, which in this case would logically be called the decimal comma.
How are some symbols used in operations on sets?
There are many ways to operate on sets. The following lists some of the more simple operations on sets, where E, F, and G are sets. ENF equals FNEEUF equals FUE, in which both are commutative operations, ENF, and G equals EN. FNG, EUF, UG equals EU, FUG, in which both are associative operations, ENF, UG equals EUG, N, FUG, EUF, and G equals ENG, U, FNG, in which both are distributive operations.
What is quantum mechanics?
Quantum mechanics is a branch of quantum theory that simply determines the probability of an event happening. Although the mathematical calculations to prove such things are very rigorous and complex. In fact, quantum mechanics is often called the final mathematical formulation of the quantum theory. Developed during the 1920s, it accounts for matter at the atomic level and is considered an extension of statistical mechanics, but is based on quantum theory. One important part of quantum mechanics is wave mechanics, which is an extension of quantum mechanics based on Schrödinger's equation. This idea states that atomic events can be explained as interactions between particle waves. For more on Erwin Schrödinger, see History of Mathematics.
What is an Argand diagram?
An Argand diagram is a graphical way of representing a function of a complex variable, often written as z equals x plus e, in which x, y, and z are coordinates in three-dimensional space and I is an imaginary number. Its true discoverer is not actually known, but Swiss mathematician Jean-Robert Argand. 1768 to 1822, is given credit for the diagram. It is thought that this was also independently discovered by Danish mathematician Caspar Wessel. 1745 to 1818, and later by German mathematician and physicist Carl Friedrich Gauss. 1777 to 1855, in 1832, but he probably determined it much earlier, thus, its other name is the Gaussian plane.
What is the Monty Hall problem?
Let's Make a Deal, a once popular television game show with host Monty Hall, who was the master of ceremonies from 1963 to 1986, is the origin of the Monty Hall problem. The same type of problem is also represented in a card game called Three-Card Monty. The Monty Hall problem is similar to the show. A contestant is given a choice of 3 doors. Behind one is a car, behind the other 2 there is nothing. The host asks the contestant to pick a door. After the pick, the host opens one of the unpicked doors. One the host knows is empty. The host then suggests a switch. The big question, and the problem, becomes, does the contestant switch his or her choice or keep the originally chosen door? The mathematical, statistical answer is yes, switch the doors. Why? Because the original probability that the contestant picked the correct door does not change. It is still 1/3. But if the contestant does switch, the probability becomes 2/3. Most people believe that once one of the doors is eliminated, the probability between the remaining doors becomes 50 to 50, but it does not.
What was the driving force behind the development of accurate clocks?
The true driving force behind accurate clocks began around the 16th century in relation to finding longitudinal measurement. As countries began to explore the world, an accurate way of telling a ship's position became a critical problem. With one time standard around the world, and clocks to tell those times, longitude, and thus position, could be determined. This would not only mean an increase in exploration but also wealth for the sponsoring country.
What is a rate?
The rate is often used in measurement. It is defined as the comparison by division, similar to a ratio. For example, when measuring miles or kilometers per hour in your car, the rate equates the pairs of miles, kilometers, with hours. The translation for a rate of 65 miles per hour is that for each hour, one will travel 65 miles as long as the speed remains the same for that hour.
Who was Adrien Marie Legendre?
Adrien Marie Legendre, 1752–1833, was a brilliant French mathematician and physicist. He is known for his studies of ellipsoids, leading to what we now call the Legendre functions, and celestial mechanics, and he worked on the orbits of comets. In 1787 he helped measure Earth using a triangulation survey between the Paris and Greenwich observatories. In 1794 Legendre published Elements de Géométrie, an elementary text on geometry that would essentially replace Euclid's Elements and would remain the leading text on the topic for close to a century. Finally, Legendre also had an important connection to measurement. In 1791 he was appointed to the Committee of the Académie des Sciences, which was assigned the task of standardizing weights and measures.
What is statistical quality control?
Quality control has been around for a while in a crude sense. When a certain product was manufactured, and consumers chose that product, the makers would try to improve the quality of the product or lower its price. The improvement of the quality did not stop with the product, but also included the process for making the product. But the use of mathematics was minor in early quality control. It was not until the 1920s that statistics was applied to industry and quality control, mainly because of the development of sampling theory. For more about sampling, see Applied Mathematics. Modern statistical quality control refers to using statistical techniques for measuring and improving the quality of processes. It is often broken down into statistical process control, SPC, see above, and statistical quality control, SQC. Both terms are usually used interchangeably, although SQC has a broader focus than SPC. To compare, SPC is the application of statistical techniques to control a process, reducing variation so that performance remains within specific limits. SQC is the application of statistical techniques to control quality and includes acceptance sampling, inspection of a sample from a lot to decide whether to accept that lot, as well as SPC.
What were the ancient definitions of a foot?
Not all feet, or the foot, are created equal. The term foot in measurement has had a long history, with many stories claiming the origin of the first foot status. In fact, it seems as if the foot has ranged in size over the years from 9.84 to 13.39 inches. 25 to 34 centimeters, depending on the time period and / or civilization. For example, the ancient Harappan civilization of the Punjab, from around 2500 to 1700 BCE, used a measurement interpreted by many to represent a foot, a very large foot. At about 13.2 inches, 33.5 centimeters, see above for more about the Harappan. Around 1700 BCE, the Babylonians put their foot forward. A Babylonian foot was 2/3 of a Babylonian cubit. There are even records from Mesopotamia and Egypt showing yet another measurement system that included a foot of 11.0238 inches, 300 millimeters. This was also known as the Egyptian foot, and it was standard in Egypt from pre-dynastic times to the first millennium BCE. The Greek foot came close to today's foot, measuring about 12.1 inches. 30.8 centimeters, a Roman foot measured in at 11.7 inches, 29.6 centimeters. The list goes on, depending on the country and time period.
How did early painters integrate mathematics and painting?
Early painters had a problem: how to represent the three-dimensional world on a two-dimensional canvas. Or, how to give paintings depth and perspective. Although perspective does follow mathematical guidelines, many early painters were able to incorporate perspective, or depth perception, intuitively. The idea of perspective flourished around the time of the ancient Greeks, who used a form of perspective to design certain architectural structures and even theatrical stage settings. But it is unclear whether they actually understood the mathematics behind perspective. One of the first to create the impression of depth by using certain rules was Italian painter, sculptor, and architect Giotto di Bondone, c. 1267 to 1337. But those rules were of his own devising and were probably not based on mathematics. Whatever the case, he clearly worked out a way to represent depth in space. And he came close to understanding linear perspective. But it took until the Renaissance before painters explored the science behind perspective. In the early 1400s, sculptor Filippo Brunelleschi, 1377 to 1446, made the first correct formulation of linear perspective using mirrors. He understood that there was a single vanishing point to which all parallel lines in a plane, or on his canvas, converge. He also understood scales, calculating the relationship between the actual length of an object and its length in the picture, depending on its distance in the painting. Writer and mathematician Leone Battista Alberti, 1404–1472, was the first person to write the rules of perspective in 1435. Using the principles of geometry and the science of optics. By 1450, artist and mathematician Piero della Francesca, 1412–1492, had written an even more extensive mathematical work on perspective, including concepts of art, arithmetic, algebra, and geometry. The writings of mathematician Luca Pacioli, c. 1447 c. 1517, or Friar Luca dal Borgo, who was also known as the father of accounting, see below, delved more into perspective, including in his book De Divina Proportion, which relied heavily on Francesca's work. The illustrations in Pacioli's book were done by none other than the famous scientist, painter, and Renaissance figure Leonardo da Vinci, 1452–1519, who was himself a great contributor to the study of perspective. Pacioli was one of da Vinci's teachers, and he instructed the eventual great master a good deal about proportion and perspective.
What is the composition of the air?
Meteorologists determine the composition of air by analyzing its various constituents. These are mainly displayed in terms of percent of the atmosphere. The first 40 to 50 miles, 64 to 80 kilometers above the surface contains 99% of the total mass of the Earth's atmosphere. It is generally uniform in composition, except for a high concentration of ozone, known as the ozone layer, at 12 to 30 miles, 19 to 50 kilometers, in altitude. In the lowest part of the atmosphere, the area in which humans, other animals, and plants live, the most common gases are nitrogen, 78.09%, oxygen, 20.95%, argon, 0.93%, carbon dioxide, 0.03%, and minute traces of such gases as neon, helium, methane, krypton, hydrogen, xenon, and ozone. Water vapor is also present in the lower atmosphere, although variable and at a very low percent. Higher in the atmosphere, the composition and percentages change as the atmosphere thins. For more about percents, see Math Basics.
Can we change the calendars now in use?
The present calendar is an annual one and changes every year, much to the happiness of calendar publishers. This is because 365 days in a year is not evenly divisible by the number of days in the week. 365/7 equals 52, with the remainder of 1, or 52.142857. This means that a given year usually begins and ends on the same weekday, and it also means that the next year bumps January 1st, and all following dates to the next weekday, and a new calendar is born each year. but because the calendar we now have is so ingrained in everything we do. It is doubtful that there will be any changes soon. Not that there haven't been suggestions. One is called the World, or World's Day, calendar, in which each date would always fall on the same day of the week. And all the holidays occur on the same day of the year. With this calendar, each year begins on Sunday, January 1st, and each working year begins on Monday, January 2nd. The reason why the calendar is called perpetual or perennial is that the year ends with a 365th day following December 30th, which is marked with a W for World's Day, our current December 31. Leap year days would still have to be added, such as at the end of June. Some suggest a June 31 be added. Both extra days could act as world holidays.
Who built the first mechanical binary computer?
German civil engineer Konrad Zuse, 1910 to 1995, built the Z1, often thought of as the first mechanical binary computer in his parents' living room around 1938. His goal was to build a machine that would perform the lengthy and tedious calculations needed to design building structures. His computer's design stored intermediate results in its memory and performed sequences of arithmetic operations that he programmed on punched paper tape. He initially used old movie film. This machine led to the Z3 in 1941. Considered by some to be the first large-scale, fully functional automatic digital computer, the computer used a binary number system.
What is the story behind Archimedes in the bathtub?
Any of the most famous stories of Archimedes involves royalty. Hiero II of Syracuse, king of Sicily, wanted to determine if a crown, actually, a wreath, he had ordered was truly pure gold or alloyed with silver, in other words, whether or not the royal goldsmith had substituted some of the gold with silver. The king called in Archimedes to solve the problem. The Greek mathematician knew that silver was less dense than gold, in other words, silver was not as heavy as gold, but without pounding the crown into an easily weighed cubic shape. He didn't know how to determine the relative density of the irregularly shaped crown. Perplexed, the mathematician did what many people do to get good ideas: he took a bath. As he entered the tub, he noticed how the water rose, which made him realize that the volume of the water that fell out of the tub was equal to that of the volume of his body. Legend has it that Archimedes ran naked through the streets shouting, "Eureka! I have found it!" He knew that a given weight of gold represented a smaller volume than an equal weight of silver, because gold is much denser than silver, so not as much is needed to displace the water. In other words, a specific amount of gold would displace less water than an equal weight of silver. The next day, Archimedes submerged the crown and an amount of gold equal to what was supposed to be in the crown. He found that Hiero's crown displaced less water than an equal weight of gold, thus proving the crown was alloyed with a less dense material, the silver, and not pure gold. This eventually led to the hydrostatic principle, as it is now called. Presented in Archimedes' appropriately named treatise, on floating bodies. As for the goldsmith, he was beheaded for stealing the king's gold.
What is addition?
Addition is an operation in which two numbers, called the addends, produce a third number called the sum. Natural numbers are added by starting with the first addend, and counting as many more numbers as the second addend. For example, for 2 plus 4, you would think 2, 3, as the first number after 2. 4, as the second number, 5, as the third number, and 6, as the fourth number. Thus the numbers add up to 6. Not all numbers are added in the same way as natural numbers.
Who were some of the most influential Ionian, Greek, and Hellenic mathematicians?
The Ionians, Greeks, and Hellenics had some of the most progressive mathematicians of their time, including such mathematicians as Heron of Alexandria, Zeno of Elea, Eudoxus of Cnidus, Hippocrates of Chios, and Pappus. The following are only a few of the more influential mathematicians. Thales of Miletus, c. 625 c. 550 BCE, Ionian, besides being purportedly the founder of a philosophy school and the first recorded Western philosopher known, made great contributions to Greek mathematics, especially by presenting Babylonian mathematics to the Greek culture. His travels as a merchant undoubtedly exposed him to the geometry involved in measurement. Such concepts eventually helped him to introduce geometry to Greece, solving such problems as the height of the pyramids, using shadows, the distance of ships from a shoreline, and reportedly predicting a solar eclipse. Hipparchus of Rhodes, c. 170 c. 125 BCE, Greek, also seen as Hipparchus of Nicaea, was an astronomer and mathematician who is credited with creating some of the basics of trigonometry. This helped immensely in his astronomical studies, including the determination of the moon's distance from the Earth. Claudius Ptolemaeus, or Ptolemy, c. 100 c. 170, Hellenic, was one of the most influential Greeks, not only in the field of astronomy, but also in geometry and cartography. Basing his works on Hipparchus, Ptolemy developed the idea of epicecles in which each planet revolves in a circular orbit, and each goes around an Earth-centered universe. The Ptolemy way of explaining the solar system which we now know is incorrect. Dominated astronomy for more than 1,000 years. Diophantus, c. 210 c. 290, was considered by some scholars to be the father of algebra. In his treatise Arithmetica, he solved equations in several variables for integral solutions, or what we call Diophantine equations today. For more about these equations, see algebra. He also calculated negative numbers as solutions to some equations, but he considered such answers absurd.
What other significant mathematical contributions did the Babylonians make?
Throughout the centuries, the Babylonians made many mathematical contributions. They were the earliest people to know about the Pythagorean theorem, although it was not known by that name. In fact, Pythagoras, in his travels to the east, may have learned about the theorem that would eventually carry his name from the Babylonians. In addition, the Babylonians possessed all the theorems of plane geometry that the Greeks ascribed to Thales, including the theorem eventually named after him. They also may have been the most skilled algebraists of their time, even though the symbols and methods they used were much different than our modern algebraic notations and procedures.
How has math been used historically in architecture?
Historically, there has been a great connection between architecture and mathematics. Ancient mathematicians were architects and vice versa, using their skills to build pyramids, temples, aqueducts, cathedrals, and a range of other architectural structures we find beautiful and awesome today. For example, in ancient Greece and Rome, architects were required to also be mathematicians. During medieval times, most buildings and structures carried some symbolic reference to the church. The mathematical end of architecture was almost forgotten during this time. By the European Renaissance around 1400, a new kind of architecture developed that emphasized mass and interior space to produce aesthetically pleasing pictures similar to those found in paintings and sculptures. This led to an entirely new way of looking at architecture and altered its connection to mathematics.
What do the numbers on gas and electric meters measure?
Gas and electric meters measure the daily gas or power usage, usually of a house or other building. The standard electric meters are clock-like devices that record the amount of usage. As a house or business draws on the electric current, a set of small gears inside the meter move. The number of revolutions are recorded by dials in the meter, with the speed of revolutions determined by the amount of power consumed. Newer digital models record power usage digitally. A gas meter measures the amount of gas used by a home or business. In this case, the meter measures the force of the moving gas in the pipeline. The dials on the meter turn faster as the flow of gas increases, or slower as the gas flow decreases. To understand how the gas and electric companies charge a customer takes only an understanding of simple mathematics. In both cases, the difference between 1 month's reading and the next month's reading is the amount charged. For example, if the electric current reading is 3,240 and the previous month's reading is 3,201, the amount of electricity used is 39 kilowatts for 1 month. Then the company multiplies the number of kilowatts by the amount per kilowatt hour to arrive at the charge to the customer.
What are logical operators in predicate calculus?
Predicate calculus commonly uses 7 special symbols called logical operators to express a formula. In this case, a formula is a meaningful expression built up from atomic formulas by repeated application of the logical operators. The following table lists the symbols and their meanings.
How is math used to understand chemical reactions?
One of the simplest examples of mathematics used in understanding chemical reactions is based on 2 chemicals, A and B. They can be molecules or ions. If A and B encounter one another, they can rearrange themselves into molecules or ions of 2 other substances, in this example, C and D. The reaction that takes place can give off or absorb energy, making the molecules move faster or slower. Although this is a simple example of what can happen in a chemical reaction, it can still be analyzed using mathematical modeling.
What is relativity?
Relativity refers to the idea that the velocity of an object can be determined only relative to the observer. For example, if a fly moves around the inside of a car at about 1 mile per hour, inside the car's frame of reference, the fly is moving at 1 mile per hour. But if the car goes past you at 65 miles per hour, it will appear as if the fly is traveling at 66 miles per hour, not 1 mile per hour. In other words, it's all a matter of reference, and it's relative to your viewpoint.